Welcome back. Today we're going to talk about matrix algebra, and matrix algebra is just a variation of solving linear systems where we're just going to use the coefficients. So we're going to get into some more advanced operations in the next coming sections, but we need to outline some of the preliminary stuff so that we can talk about matrix algebra and matrices in general. When we talk about an m by n matrix, m by n is rows by columns. So for example, if A is equal to 2, 1, 5, 4, 6, -2, right? It would be A is a 2 by 3 matrix. Okay, it's a 2 by 3 matrix because it has 2 rows and 3 columns. And so when we determine the order of a matrix, that means to tell its dimensions. And so in A, we're going to have 1, -2, 3, and then 2, 0, 4. So it would be 2 rows by 3 columns. This is a 2 by 3. Determining the order of a matrix becomes important because when we're going to multiply in a few minutes, we need to be able to determine if they're actually able to be multiplied. So for the next one, 1, -1, 0, 14, 2, -1, and then 3, 62. This one would be 4 rows by 2 columns, 4 by 2. Okay, so you get the idea of that, counting the rows and the columns. When we add and subtract, it's important that they have to be the same. They have to have the same order. Must have the same order. So, for example, A plus B, when these are matrices, if A is equal to, let's say, 1, 2, 3, 4, and B is equal to 5, 6, 7, 8, in order to add and subtract them, so A plus B is going to look like this. So 1 plus 5, so that's going to be 6. And then 2 plus 6 is going to be 8. And then 3 plus 7 is going to be 10. And then yellow is not a good choice. 4 plus 8 would be 12. Okay, so you add up the matching elements to get your sum or your difference. Okay, scalars, so that would be like 3a. So the scalar would be 3. So 3 times a would be 3 times 1, and then this would be 3 times 2, 3 times 3. It's times each individual element. So it's going to be equal to 3, 6, 9, 12. Okay, so you multiply the scalar by each individual element, and we use it in that way to multiply out. So when we find the following, this is notational. Okay, the subscript tells row and column. And so for this one, the rows and columns, so this is right here, this is A1, 1. This is so row 1, column 2. This is A1, 3. Okay, so row 1, column 3. This is A2, 1. This is A2, 2. This is A2, 3. Okay, so that subscript, so below the line, means row and column. So if I'm going to find A1, 2, that's going to be 9. A2, 1 is 8. A11 times A22, so those two are going to be a product. So A11 times A22 would be 4 times 3, which is 12. And then 3 times A23 would be 3 times 10, which is 30. Okay, so that's how that works. It's really just a matter of identifying. It's a lot of notational stuff, a lot of identifying individual elements and being able to use these operations to operate inside of these. And what you're going to see is as we tie the matrices to systems of equations, you can multiply an equation by a scalar. That's no problem. In a matrix, it's just the same. All right, so now we're going to do some matrix operations, and they give us two matrices. So normally what will happen is they'll give you one, maybe two, one or two, maybe three matrices, and they're going to ask you to do a bunch of things with them. I'm going to do a couple of these because we kind of saw how this operated, but I don't want to gloss over it because it is important to be able to follow this through to the very end. This is useful on spreadsheets, looking at huge sets of data that need to be organized specifically. So here we go. When we do A plus B, that's adding individual elements, and it's really just keeping track of things. So A plus B, we're going to add elements that correspond. So it's going to be 5 plus 2. My next element is going to be 4 plus 5, then 6 plus 9, and then 3 plus 9. And so when I break this down, I'm going to have 7, 9, 15, 12. So on our next one, we're going to subtract, and the process is the same. So we'll do 5 minus 2, so that's the first two elements, and then 4 minus 5, 6 minus 9, and 3 minus 9. When we simplify this, we're going to do 3, and then minus 1, and then minus 3, and then minus 6. Okay? Simplifying those elements individually. Negative 5a is a scalar, so I'll have negative 5 times 5, negative 5 times 4, negative 5 times 6, negative 5 times 3. So we have negative 25, negative 20, negative 30, and negative 15. That's a scalar. The next one would involve multiplying a scalar by each of them and then going ahead and adding them. So I'm going to put 4a over here, 20, 16, 24, 12. 3b, got to be careful on that. 3b is equal to 6, 15, 27, and 27. So when I add these, I'm going to have 20 plus 6 is 26, 16 plus 15 is 31, 24 plus 27 would be 51, and 12 plus 27 would be 39. Okay, so that's how the process goes. Keeping track of those elements, making sure you multiply your scalars correctly. Zero matrix. The zero matrix is all zeros. Okay, so it's all zeros, and that would be like to the point where A plus the zero matrix is equal to A. Additive identity, that's this. Okay, zero is the additive identity. Additive identity is so x plus A is equal to A. Identity means it gets itself. So 0 plus A is equal to A. So 0 is the additive identity. 0 is the additive identity for matrices as well. Additive inverse. The additive inverse is where A plus B equals 0. And so B is equal to the opposite of A. So for example, if I had A is equal to 2, 3, 4, 5, then the opposite of A would be negative 2, negative 3, negative 4, negative 5, such that, and so negative A, so this is B, so B is equal to negative A, meaning all of the elements are the opposite. So if it's negative 2, it would be 2. If it's 2, it would be negative 2. And so then A plus B would be equal to 2 plus negative 2, 3 plus negative 3, 4 plus negative 4, and then 5 plus negative 5. So what I would end up with is A plus B is equal to 0, 0, 0, 0, which is my zero matrix, is my additive identity. All right, let's talk about products. Products are a little bit of a tricky process if you don't keep track of everything that's going on. Okay, so for products, for matrix multiplication, if A times B works, okay, meaning you can do it, then you have to have matching orders, sort of. So parts of the dimensions have to match. So for example, if A is a 3 by 2 and B is a 2 by 4, you got to put them next to one another. So A, B is, it looks like this. It's a 3 by 2 times a 2 by 4. These have to match. So insides match. Outsides are the order of AB. So A and B can be multiplied because the insides match, and the product is going to be a 3 by 4, 3 rows by 4 columns matrix. And so if we're going to look at find the product AB where possible, we got to check to see if it works. So A, this one is a 2 by 3, and this one's a 3 by 2. And so my middles match. And my outsides, these are the dimensions of AB. Okay, so that's the dimensions of AB. So here's how it works. AB is equal to, now, this right here, row 1, column 1. So in this spot here goes row 1 times column 1. What does that look like? Well, it's going to look like this. Row 1 times column 1. So it's going to be 2 times 1 plus 1 times 0 plus negative 3 times 1. And so that's equal to 2 plus 0 plus negative 3. So 2 minus 3, which is equal to minus 1. So I'm actually doing a simplified version here and then my final answer here. Next spot. Because this is a 2 by 2, right? So the answer is going to be a 2 by 2. So I'm really going to have 4 parts that I'm finding. So this one right here, this element is literally row 1, column 2, right? Because it's first row, second column. So it's going to be row 1 times column 2. So 2 times negative 4. And then 1 times 2 plus 1 times 2. And then negative 3 times 0 plus negative 3 times 0. So that'd be negative 8 plus 2 plus 0. Negative 8 plus 2 is negative 6. This element here is row 2, column 1. So it's going to be row 2 times column 1. So I've got 0 times 1 plus 1 times 0 plus 2 times 1. So that's a 2. Carry it all the way over. This element here is row 2, column 2. So it's literally row 2, column 2. So row 2, 0 times negative 4. So that's 0 times negative 4. Plus 1 times 2 plus 2 times 0. So that's 2 and 2. Okay? That's all there is to it, guys. So, I mean, I don't want to oversimplify it, but at the same time, it's a lot of keeping track of exactly what's going on. And as you go through, if you lay out exactly what it is, and then you perform those operations in sequence, you get the right answer. Okay? The identity matrix is the multiplicative identity. So for example, A sub 2, meaning for A sub 2 is a 2 by 2 matrix. Okay, it's a 2 by 2 matrix. So the identity for a 2 by 2 matrix is 1, 1, 0, 0. So ones on the diagonal. So A2 times I for 2 is equal to A. Because if you multiply it out, it's going to be equal to the same thing. Okay, so for example, I3, the identity for a 3 by 3 matrix, is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. So you can see I've got my ones on the diagonal there. I4 is equal to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Ones on the diagonal. Singular versus non-singular matrices. Well, let's talk about just in the identity matrix for just a minute. The identity matrix is a goal of ours. When we start to do some row operations, we're going to try to see if we can make these into some, like, into this form, and it's going to help us solve equations. So identity is very important eventually, because what it essentially ends up with is all the coefficients are 0 except for the 1, and that's going to be a single variable. So we're going to talk about that more in the coming section. So don't discount the fact that that's a thing. All right, so inverse. Let's talk about inverse for a minute. An inverse is a matrix that, when multiplied with another, has a product that is the identity matrix. For example, A times B is equal to I, so B is equal to A inverse. Okay, so that means when you multiply them together, you get the identity matrix. And so it's possible sometimes to find an inverse for one, and sometimes it's not. So if a square matrix where M equals N, meaning 3 by 3, 4 by 4, a square matrix has an inverse, so you can find something such that when you multiply them together, you get the identity. It's non-singular. Which means singular has no inverse. So singular matrices have no inverse. So we're going to verify that matrices are inverses. I'm going to give you two matrices. A is equal to 3, negative 2, negative 1, 1. And B is equal to 1, 2, 1, 3. So that would mean that A times B is equal to the identity matrix. So I'm going to put a question mark over that, meaning, is this true? So let's try it. A times B is equal to, and I've got 2 by 2 and a 2 by 2, so these match, and my answer is a 2 by 2, so I'm going to go like this. Row 1, column 1, row 1, column 2, row 2, column 1, row 2, column 2. So let's do a little multiplication here. Row 1 times column 1. So 3 times 1 is 3. Negative 2 times 1 is negative 2. And then row 1, column 2. So 3 times 2 is 6. Negative 2 times 3 is negative 6. Row 2, column 1, row 2. So that's negative 1. and then 1 times 1 would be plus 1. And then row 2, column 2, so negative 1 times 2 is negative 2, and then 1 times 3 is 3. Simplify. 3 minus 2 is 1, 6 minus 6 is 0, this one's 0, and this one's 1. So I just verified that those are inverses because when I multiplied them together, I got the identity matrix. Does a matrix have an identity? Does a matrix have an inverse? Okay, so we have to determine that, and there's a formula for it. So the inverse of a 2 by 2 matrix looks like this. Let A be this matrix here. A, B, C, D. If my cross product, the difference in my cross products does not equal 0, so AD minus BC does not equal 0, then A, B, C, D, and this is the formula, this is the notation for inverse, is equal to 1 over AD minus BC times, so this is a scalar here, times D negative B negative C A. So what happened here? So this is called a scalar because it's going to be a number. So you'll notice, like, it's hard with letters sometimes, but you'll notice here we've got a fraction, so this can't, that's why this can't be 0. This is a scalar, and then D and A switch, and then C and B become negative. And so when we're looking at inverse, this is going to be the inverse of it. Okay, and you can use your calculator to find this, but for a 2 by 2, you need to be able to do this by hand. And so the determinant is this AD minus BC. Okay, so that's the part that can't equal 0 because it's on the bottom. Okay, determinant of anything else in calculator. Under the math menu. Actually, it's under the matrices part, but it's going to be this, det. Okay, the det function is the determinant, det. Okay, and that's how we're going to find the determinant of A. All right, so to find the inverse of anything else, we're going to put in the calculator. We're going to put the values in the calculator, and then do A, and then do the minus 1. This is going to be the inverse. Okay, so that's how we're going to do it. You should be able to do a 2 by 2 by hand. You should be able to do the determinant and the inverse of a 2 by 2 by hand, but you should be able to do the determinant and the inverse of anything else using your calculator. And I'm going to link a video here in the comments of this video. Okay, so thanks for watching, guys, and we'll see you next time.